So welcome everyone for lecture 3 for cloud computing and big data. The topic today will be Apache Spark for cloud applications. And Apache Spark is certainly one of these data analytics packages, which is very well known and almost everywhere adopted in cloud computing. It has huge overlaps with many of the different Apache stacks that you maybe already heard about, Hadoop or Hive, and lots of other of those which are basically open source. Maybe I can do a quick round. Who has used Apache Spark or heard at least from Apache Spark before? Okay, from Apache Hadoop. Hadoop distributed file system maybe is also very known. Okay, this will come in subsequent lectures. So we go here a little bit out of sync to get you early access to the assignment 1. That's why we put Apache Spark a little bit first before we went off to basically MapReduce and other elements in the next couple of lectures. But before we start into the material, basically into the lecture today, let us review a little bit what we had the last time. And the last time was really a very, let's say, nice introduction, not really requiring any prerequisites essentially for learning machine learning basics. And interestingly enough, what you learned there was the perceptron learning model, which admittedly is a linear learning model, so very, let's say, simple, or one of the most simplest learning model, if you will. It's still the basic ingredients of cutting-edge deep learning networks today. Of course, there are other activation functions, and you stack lots of these neurons together and lots of deep layers. But in the end, you learned a little bit the basics, which also will appear again in lecture 8 and lecture 9 when we talk about cutting-edge deep learning today. We focused a little bit last time on classification. Machine learning has much more to offer. Maybe I can just also ask, who's using the machine learning course here at the university? That's quite a nice complementary topic. Perfect. They go much more in deep detail, learn probably much more learning models than we can probably cover here. But of course, what you learn there is basically equally transferable here. So we focused on classification, and there we had this interesting idea of this flower classification, if you remember. So which is essentially one task of a machine learner. We basically want to do something and automate the process. Maybe a very specialist in basically flowers or in biology can distinguish this flower, if you remember, of saying, is it an Iris setosa or Iris virginica? But basically, we as normal people that maybe just have a phone and want to make a photo and want to know what flower that is, have maybe no idea if it's this or that class. And this is a kind of pattern where you think this flower must have some form of a pattern inside, a pattern we don't know, but we want to search for. So this is a basic key ingredient. You have something which seems to be not random. So there seems to be something giving us a learnable kind of pattern, which basically brings us then to machine learning. The other part is, of course, if there would be an exact mathematical formula for it already, that let's say some genius already had a perfect formula for Iris setosa, Iris virginica, then we just use Python, implement it, and do it. There's no point going through all the data sets again and again iteratively using the perceptron learning model, etc. So of course, if you have a perfect formula, go ahead and implement it, right? So that is also, if there's no exact mathematical formula, then machine learning to the rescue, we couldn't learn from data. And this is of course the idea then in the third part, as we say, the most important ingredient, if you want, of course, for machine learning, because that means nothing else than learning from data. If you don't have data, then it's hard. If you don't really swim in data or the data is too noisy, chances are you cannot really do machine learning, right? Things which probably also are taught in the other course, noise in the data sets and things like that. Right, we focus then a little bit on this perceptron learning models. That means you basically have the constants, which are our data set, right? The x1 up to xn in terms of the different features you have basically in your data. And the good news is we focus a little bit on supervised learning. So supervised means we have the output given as well where we can learn from. And this enables us to get quite good modeling, while unsupervised is much more harder to do. And basically also reinforcement learning has its, let's say, problems. Here in the supervised setup, many of these learning parts are really well understood. So there you can basically learn quite well if you have enough data. Right, and this is basically now the idea that came out in the 60s. So you sum them up linearly using these weights, right? So similar like the human brain neuron, you basically take all the different data sets, you run that through a certain, let's say, function. Here it's a step function, if you remember, -1 and +1, saying just, is the minus or plus. in terms of the signal that comes through. And we modeled this a little bit here using linear algebra in very simple terms, which means nothing else than shifting a line essentially through the 2D space here. And how we shift the line is this red thing, right? So the red element, the weights we have to learn. And we simplified this a little bit of saying the bias is something we also don't have and want to learn. And when we model that as always 1, which we can do because we can learn the x0 here, basically, apart from this, if you model it like this and put it into this W transpose X, which is more mathematical convenience to do the same, essentially, formula that you see there, a bit more compact. So by doing so, and now using this perceptron learning model, we have seen we need something else, right? That is interesting. Now we have an idea how the model looks like, but every time you have a model, there should be a learning algorithm follow suit, right? There's some that you combine it. If you have support vector machines, there would be quadratic programming. If you basically have neural networks, there would be backpropagation of error. So they have all the learning algorithms. And for us, it was a perceptron learning model combined with a perceptron learning algorithm. There are also some other algorithms that you combine with the linear learning model, but we focused on the simple perceptron learning algorithm. And we have seen by iteratively doing this again and again, and if the data is linearly separable, so if you can really divide it by a line, then we have seen it converges. This was this one, illustration. And by doing this with the output, of course, we can always control and check if our model is correct, because we have for each given input, the output. Now, for those of you who are in the machine learning course, know also it's not always that simple. You have training sets, test sets, you have validation sets, and so on. But of course, for the simple, let's say, idea we had the last time, it was quite sufficient, and it worked. The truth is there's a third, basically, flower type, which is versicolor, the iris versicolor. If you put that in the equation here, it wouldn't work because the data would be not any more linearly separable. They overlap. Basically, there's no dividing line and the perceptron learning algorithm would fail, right? But I left that out. Maybe the machine learning course should talk about this much more than here in the course. Now, the interesting thing is in the linear learning model space, you can combine now many of these different findings with a neuron and putting that in a different context. One of the ideas we had learned last time is then not just basically doing a +1, -1, but rather a kind of space between 0 and 1. It's a logistic function that you see here. So you squash the signal that comes out. Basically, instead of saying roughly +1, -1, which is more stepwise, we have a very smooth way of classifying it, but still having a binary classifier. So saying basically we have a 2-class problem. And that's what we had the last time by looking a little bit on the different roles that we had here for all the different people, and had done a model in the second part of the course, which have then used this logistic regression model essentially to predict a little bit, would these people really be doing a bank deposit or not? Based on historical data, that is the idea of machine learning. So again, there we think somehow the people, in terms of their personalities, in terms of their jobs and their features, some have a pattern. There was no formula of saying, well, the musicians always deposit a lot of money. So there's no mathematical formula, but we have lots of data from the bank, from previous people depositing. So essentially a typical machine learning problem, a very simple algorithm is binary classification. Will they deposit? Will they not deposit? Now, those of you that have been in Harper when I'm presenting, you have seen we have 54 classes in satellite imaging, or those that basically do here, the course with Gabriel. It's much more complicated in practice and in science and engineering. But of course, here you have the simplest learning models to really understand what you can do there with machine learning. And of clouds, we are of course now interested in speeding these things up. So we don't want to have scikit-learned Anaconda, we want to it at scale. That means the processing, this learning iteration, basically that's something that we want to do much more quicker. And of course, in terms of data, when there's really big data, then of course, many of the laptops would fail. You want to go to larger clusters. And that's something of the topics I will explain today, because we didn't really touch on Spark the last time. We didn't really touch what RD Insight now is really. And we tried to do some of the theoretics today in this lecture, but in the practical situation, basically in practical lecture 3.1 on Tuesday. So it's kind of a combined lecture really, but also really relevant for your assignment 1, where you do the same thing with a provided RD Insight server. So let's do the outline a little bit. We will see Spark is of course a very big framework. This means you can do a certification of Spark even, or having a course just on Spark, right? A complete university course, no problem to have a Spark course. But of course, for the sake of more general aspects here and more frameworks and more approaches, we focus here on several unique selling propositions of the Spark capabilities. One of it is in memory, and we will learn that this is, of course, a very powerful method that gives you quite some speed up, for instance, compared to traditional approaches with the Apache Hadoop parallel performance. We also will see that Apache Spark will come with quite some interesting libraries. Once you do machine learning, you want to have some advanced algorithms. Of course, they should be already implemented to scale up. Just throwing scikit-learn, basically, with the serial implementations onto a cluster will not work. It's not parallelized, right? It's also part of the course. We need parallel algorithms to leverage a parallel infrastructure to scale high, right? And to make big data work. And this is a part of the second. When we look a little bit into different problems, the machine learning lib in Apache Spark is very rich, but of course covers not everything today, especially not deep learning networks. You will see that in lecture 8, lecture 9, we will come back to machine learning in terms of deep learning, so TensorFlow, PyTorch, and much more other packages which are, mastered deep learning also at scale, combining this with Horovod and so on. But here we really focus on Spark. So there are some of the traditional learning models which are still very well supported and parallel possible. We will look a little bit on other problems like graph problems. More and more these graph, let's say neural networks and also graph problems are really an apparent part of machine learning, especially where structured data on a mesh type or on a, let's say, typical SQL table or relational database table, if you call it, is not given. So this is also very helpful to have their libraries which helps these particular applications. We will look in one of them when we think about basically how you would rank websites probably. This is also a good example that this is not a complete normal table because it's a really mesh, what websites look and point to other websites. Here and there are some business applications and videos, as you know, for lecture 3. So the basic capabilities of Apache Spark is really being open source. That's for one thing, a very good thing. And the second one is surely to leverage really memory processing. So we'll talk about that a lot. And if you now look into Google Dataproc, into Amazon Web Services and MS Azure, no matter which cloud you basically look in, there will be a support for Apache Spark, right? Probably this will be in different versions, 2.3, 2.4, but basically you see that this is everywhere available. Now, the interesting thing of these Apache stacks that you have usually like Spark, like Hadoop, is they work very well together with others. So one of the other big elements where Apache Spark is built on is the so-called Hadoop distributed file system. But teaching that all in one place here in one course is not really possible. That's why we have the next subsequent lectures 4 and 5, talking about MapReduce, talking about the Hadoop distributed file system again. So in the end, a very interesting material. The cloud vendors change the support for Spark every now and then, but we see a little bit of trend of getting more stable, and this is also good. Needless to say that you also can access this with Jupyter notebooks. If you remember a little bit, practical lecture 01, where we had this kind of GUI, right, to access basically Python, is also these days quite nicely supported. So in way, now we start a little bit for your assignment of doing it a little bit more faster with Spark so that you get a, let's say, quicker exposure than just waiting for lecture 5 and then basically starting with assignment 1. This is something what we learned basically in the last 7 years teaching this course. And when you look basically and compare it with the so-called Hadoop that you will also basically explore more and more, you will see that essentially Spark has one key capability, and this is this in-memory processing, right? And if you know a little bit about, using the file system all the time, dropping elements and, in between results of machine learning, perhaps to disks, this is very slow. Now, what Apache Spark is doing, it tries to get as much done in memory as possible, right? And this is, of course, something which is very important, enables you with lots of actions. But there's, of course, one key consideration that you have to think about. You have to have the memory. And this is, of course, a critical factor if you go to clouds now, because you will basically swipe your credit card to get a certain amount of cores, a certain amount of memory. Memory is, of course, very expensive, right? So you have to have the infrastructure right to really use Spark in memory. In other words, you have here a framework which is very nice and fast, but you go there in the clouds and pay the price for it because you have to have lots of memory to support it. We will see how that materializes in a couple of slides more as well. But one of the key elements you see here is then to really make enormous speedups compared to Apache Hadoop, for instance, just by using Spark. Here's, I think, logistic regression, again, a simple, let's say, toy problem in machine learning, but still you have a massive difference. However, you can also understand the massive difference here means you have to probably invest in basically CPUs that have a high number of memory. And we will see soon with some concrete numbers in Amazon that this could cost for a startup quite some money to do that. So again, we are in the conflict of saying we want to have it faster, but of course, then we have to also pay for it. Another element basically that you have to see just before we come to your question is the idea is the same with Hadoop and Spark to think about more the transfer is something we want to avoid. So we're looking on getting actually the compute to the data rather than, doing large of transfers to a big HPC machine and then do huge jobs over 24 hours, over 48 hours. So here's the idea that you see a little bit here where we think about Facebook accumulates a lot of data. We all in the different supercomputing centers accumulate a lot of data. Industry at large accumulates more and more data. So sending petabytes over internet lines is incredibly hard, especially if you do more and more of these and constantly. So here's the idea is having rather smaller jobs and accumulate this data decentralized. This is a little bit what this picture suggests. A question? Yeah.
Yeah, I was wondering if Spark is capable of using GPU.
Very good question. I repeat it for the audience. So there's a question here from the audience if Apache Spark can also leverage GPUs. And this is actually true. The point is it needs to be in the algorithm that is implemented. The general, let's say, framework, you see that a little bit on this slide, has just basically the basic core of having the infrastructure right, which means the basis of HDFS has a certain RDD structure, data frames, they can distribute, resubmit jobs. It's an engine to really create the jobs. What you then have is in terms of leveraging GPUs is in your hands. So you need basically implementations in these to leverage GPUs. And this is a tricky one because basically GPUs are good for deep learning. And as I said, MLlib, for instance, is not really good for using this deep learning. You would rather go the TensorFlow way. So essentially it is possible to use it with Spark, but essentially in these days, especially when using deep learning, for instance, which leverages GPUs a lot, you would rather not using it with Spark in that MLlib sense, but using Spark on the bottom, basically for the kind of distribution of the data and access to the data and reliability. And on top, put TensorFlow, for instance. That is then leveraging the GPUs that you distribute, basically. On the other hand of the scale, of course, your question also you have to think about, you have to pay, right? It depends on you how the resources are picked. And we will learn this in the course. Basically, whenever you pick a service in Amazon, in MS Azure, you will go one level deeper and say, hey, which computing resources you want to select? Is it a typical CPU with lots of memory? Is it a GPU with how much? Is it a V100, A100? You pay more price. So that's, of course, dependent on that as well. You have to pick the right resources. But I show some examples. A very good question. So in this sense, it's a big data analytics framework and should be also understood as very different from simulation sciences, what we teach, for instance, in HPC, where we rather want to really have a very interesting connection between the cores, very lively interactions, right? We always communicate every little time step. If you do weather prediction, every tile in the domain has an impact on your neighbor. In these frameworks, you wouldn't do that. You would analyze, let's say, a big pile of documents, how much actually sport documents are there, how many politics documents are there. You can basically do this in parallel and then end up the results in the end. So this is something where these frameworks are for a specific purpose and also not for, solving all questions in the world in terms of computing or especially also in terms of machine learning. So again, the basic properties coming a bit back to the question that we had, there's a whole runtime of Spark, a scheduler, a driver that is basically then leveraging the different workers. If you remember, our idea is now scaling up. We don't want to compute anymore in a small laptop. So we need 20 CPUs, 40 CPUs, 60,000 CPUs. Basically, we scale up with this. So you need some manager to manage all of these resources, right? Otherwise, in the cloud, you would maybe pay for it, 1,000 CPUs, but then they're lying there. And you have to program to use all the 1,000 in parallel. So what Spark gives you is the engine of basically working with this and managing these thousands of CPUs that you, of course, have bought with a specific structure and with nice APIs that, of course, abstract a little bit from that. So you see sometimes here with the APIs, and there are different examples, you would see if you have a very, let's say, condensed idea of using Spark, you would say you read a text file and you have really no idea where in the workers and so on, how this is distributed. You have a very high level way of implementing this. For instance, here's a filter. You want a text file, let's say a log from some website, and this has maybe several terabytes and you want the answer in 1 minute. So basically you say just, okay, search me all the errors and basically, map that out and give me a nice list. So you have here a very nice Python way of implementing it. The Spark runtime comes with a Python API. And the beauty is when there's any error here, that is a little bit the point of this resiliency. Distributed data sets, if there's a failure in some of these, for whatever reason, Spark engines try to resubmit the job. And this is quite nice. So basically giving you the opportunity that not the whole job has to be started from scratch. And with this, you have some interesting data pipelines that usually people use. Have you used pipelines maybe in the machine learning course? It's also a very good concept usually. Pipelines like data preparation, data engineering. Before you even come to machine learning, you do feature selection, feature engineering. You massage the data a lot to get to a point where you throw in machine learning and then validation on top of it for model selection. Maybe it's changing some regularization parameters. It's a pipeline, right? And then, of course, you want to use it for inference once the model is trained. So you have another pipeline for inference to basically avoiding the training step, but the same idea of doing the data transformations. So for this, Spark is quite good. And the engine really helps you a lot with redundancy. You see there's a little bit also what possibilities are there, which is a little bit alluding to the map and reduce ideas we have then in lecture 5. We will talk this about, of course, much more in detail in the next coming up lectures. But here you see also that the memory with cache partitions is something where Spark is optimized. This is, of course, an abstract idea of what you want to compute here, but often it is a, you would say, workflow graph or a pipeline graph coming from different areas. And then, let's say, predefined operators that you can use in Spark quite nicely. And if there's an error in this way, as I said, also the kind of automatically resubmission of basically Spark is quite nice. And by doing all the stages, you see it tries to reuse memory as much as it can. Of course, it's limited, right? The space is limited in memory. That could mean, of course, like here, an unlucky situation that here you cannot leverage the complete cache because there's just not enough space available. Still, this already, is basically speeding up the process quite a lot. And especially here where you have everything cache already. So these are just examples to get more and more into the message how you program Spark, which is quite nice because you don't program it like we do in HPC, right? So core 1 has to do its message to core 3. Okay, when we've done this, we do maybe a broadcast to all the cores. So when we do a maybe message same with core 7 and core 1000 there on the corner, this is much more the HPC way of doing it. In Spark, this is all transparent, right? You just have workers and a head node that basically then would basically steer and manage, but the rest of computing is rolled out to the cluster and coming back on this kind of pipelines and workflows you define. And with this, it's very nice to program, right? The kind of distribution aspect in it, the parallel aspect is hidden from the user. And with this also the scalability, you can decide as a startup, do you want to have 20 workers, 40, 100? And of course, it makes it faster. At some point in time, of course, the computing or the data is so small that you don't get a speed up, right? By adding 40, 60, 80, 100 CPUs, maybe you don't need that. But in the terms of big data, this is easily scalable while not changing essentially your implementation. In HPC, that's quite different here and there. So here you see a little bit some examples where you want to do some domain decomposition of, using then the runtime from Spark. We will talk more about in 3.1 and also, of course, in the next subsequent lectures in your assignment. But you basically have a parallelize option here, so which gives you then a nums, which is already then prepared to run on parallel on a big cluster. And here are some predefined function. You have a map function basically that gives you then from these nums, for instance, all the squares. I think that's pretty obvious. You can have here a filter that says, okay, you basically want to filter out. But what this suggests is there's a very simple idea of functions, if you remember. It's not so complex of having physical formulas, implementing weather forecasts and so forth. Here, you want to filter data, map data to some more, let's say, smart ways, but not having a very complex task on all this data, because this is just more for throughput, for analytics on the data. And the same is true here when we said about the square. So this is a modular operator, obviously, that we're working on, for instance, just giving us a 4. And here we have essentially a range. Remember that this is here going on the nums. So we have 1 and 2 and 3. And then always goes basically to the range of 0 to the -1 of this. So we have 0, 0, 1 for 2, and then 0, 1, and 2 for 3. That could be index generation for some machine learning problems, all quite nice and nicely supported without thinking at all in parallel, right? Spark will execute this in parallel, of course, of much more bigger data sets, not the small that we have to do here. Another sort of actions that you can take is, of course, summary statistics. We will call that here and there. You want to have to collect some elements back to the local collection to do some statistics. You take a couple of first elements, you count how many data sets are now left after all the filtering, after all the mapping, after the massaging of the data, and reduce maybe with some very simple functions some of these materials. And of course, in the end, when you have done all of this processing, you want to have a result to file. Of course, it enables it, but the idea of the Spark runtime and of the framework and the workflow is really leveraging memory to the maximum degree. So you want to avoid dumping things to file. Only maybe as a very end, if you have your results, then you save it as a file, and then of course report it, print it out, go to your boss and say, here's a solution. So, and this brings us to the difference and why Spark has been succeeding, basically of being one of the most important, basically analytics frameworks that you have today. It really uses a lot of memory. And there was a complete generation before just using Hadoop, basically, which was a very similar analytics framework. We will learn about this also in next coming lectures, where you have always a Hadoop distributed file system where you read, and then you have it in memory dumped to disk, right? After each of the small operations in Hadoop, you always have read, map reduce, dump to disk, read, dump to disk, dump to disk. So this is what this suggests. And this, of course, is very slow. If you drop every time after you compute anything, in some iterations, let's say it machine learning, right? You do this kind of thing that we discussed with a simple perceptron model. After each iteration of the data, you have basically updated the weights, dump to disk. If you keep that in memory, what you can, for instance, in the perceptron learning model, it's actually not so tough model that it fits easily probably in the memory. You are just very fast of always reading from memory. Of course, I think many of you should know that memory is much more faster, but this framework is really leveraging this, giving us then also these performance that you see here, that basically for a simple logistic regression, it's orders of magnitudes more, right, of just using Spark in terms of Hadoop. Now there's a catch in this: big data, big memory, right? Again, I said you have to buy the resources that really fit. So hence you have some numbers, right? And this is, of course, here and there going up, and there's some very smart tricks that you can have to have on-spot resources here and there. And there's some tricks to really get, let's say, a little bit discount from the data that you see here right now. But you have to see, like when you go to a typical EC2, and you would say, well, that's something where I would be interested in taking this. You see already that when you take some memory alongside it, here you see the memory, right, for this particular EC2. That means the computing resource you can now pick. It's you picking that. So how much performance you really want to have underneath the Spark cluster, how much you are willing to pay with your credit card. Right here you see the difference when you then suddenly have 4 gig. This means 0.0 something per hour. So you would laugh, right? Would say that accumulates, I can easily finance this. But now if you think about, you would have, let's say, this 16 large as an example here, which is already quite some gigabytes, still maybe not enough, but there you go with $2.8 an hour. Now this is also giving you, let's say, 64 cores. Now if you want to have 1,000 cores to do a real world problem with a big data, then you can multiply, right? You so many per hour. And then you easily sometimes at $50 per hour. Also doesn't sound much, but think about that. Of course, you want to have this as a constant service, always running, always analyzing, and you quickly accumulate 24 hours per day times $50 for a startup. This could mean a lot quite quickly. And then there are very specialized ones you see here, memory optimized, and there's actually no limit. There are even better ones these days where you then go to $26. And these were, of course, the ones where you now think if you want to have Spark really, really fast, right? So this is not the trade-off you have to do. If you want to have it really fast, then you have to have these memory optimized resources. So you pay a lot, but at least you can give the results in an order of, let's say, seconds maybe, while here you maybe have an hour to wait because you just have, let's say, not enough memory. So it has to dump to disk every now and then because memory is just not enough. And this is now the dependency. Although you have a very nice shiny service layer with Spark doing everything automatic, take away the message, you always as a payer in clouds swipe the credit card for something. And this is not only service usage, this particular Spark cluster, also the enabling infrastructure underneath. And what I left out here is storage, right? This is just the compute part. You also have to swipe your credit card for storage, what your assignment will also look on. Right, but in the end, I mean, it looks like we pay a lot, but of course, you can put that in your price portfolio. If you have a good service for your customers, you put this margin that you have to pay the cloud, of course, in your product price. They swipe the credit card for your service and they pay for you the cloud infrastructure. That's how you should, of course, do it. But of course, it's something to consider, right? So quickly, especially as I'm always saying, you always have to think about that this infrastructure costs if you use it or not, right? So then the Spark cluster is running, it's ready to run. They usually charge you as well, right? All the time, 24 hours, even if someone is not using it. So basically you being responsible in the company have to really shut down, lock and stop it if nobody is using it. Right, a little bit more on the distribution aspects. I said already this part, we need some manager that is really now thinking about all of these jobs. In the end, how it works is it cuts all this RDD objects with all of these interesting, very quick idea of how you program this into a real, directed acyclic graph. This is this DAG, and then split all of these in different sessions and stages on a Spark cluster. And by keeping track of all of these different parts, that's where you basically need the driver program for, or the hat as it is sometimes called, because the workers are basically very stupid. They just execute what they told to in terms of the DAG parts, but the managers then basically take and keep the connections between all these, and especially if something fails because the data could not read enough quickly or whatever, it will try to resubmit and will see, well, this was not working. So then the next part of the graph should not be executed because we still wait for another one. Then when you come to the lowest level, of course, there is just in the executors here in the Spark executors, the workers, as I said, very stupid tasks, which maybe then could be just the map that we discussed, have a kind of square root taken, very simple tasks. But think about it, you do this of hell a lot of data, and this is the idea here, basically. And this brings us a little bit to the overlap of Hadoop. So Hadoop has a yarn scheduler, which was in the beginning of Hadoop also not existing. So it's quite nice to have this now. It was derived from the high performance computing domain to really have a scheduler. In former times, it was much more a simple list to be executed. Now you have with this Hadoop and yarn, basically a very nice resource manager that you can use and that always keeps track what you do on all these different nodes. There are different parts of nodes. Basically, we will talk about this more in the next couple of lectures when you think about the data. Today, we're looking much more on computing. What we forget is a little bit is the Hadoop distributed file system, the idea of the data. You want to position the job where the data is. So you have to have the data in different blocks, maybe replicated in different areas. And this is something where also then the resource manager and the scheduler helps a lot. And yarn is something which is basically helping you a lot in this. Now, when you now think, we talked about MS Azure in the last lecture, I said, well, there is, of course, HD Insight. Of course, now when you go to Amazon Web Services, if you go to Google Proc, for instance, you will find the same idea of basically having Spark alongside many different other open source tools. Here in Amazon, we call that Elastic MapReduce. Elastic suggests, again, you can scale up, scale down the Spark cluster. And there are lots of other ones, Amazon Redshift, Elasticsearch services. There are lots of these services that you can nicely combine them essentially with these services of creating a higher value. Here with this Elastic MapReduce, you have basically Hadoop, you have the Hadoop distributed file system, Hive, a lot of big data ecosystems. We also will talk about, of course, in subsequent lectures. We just cannot push everything in one lecture because it's just a very, very huge stack of open source tools. Just to get the idea that when you, for instance, want to port basically from MS Azure your Python code, chances are you can do this easily with Amazon Web Services in the Elastic MapReduce. And there you have also basically Apache Spark, Hive, Presto, and lots of the other big data frameworks we will talk about in the course. So usually you have a Spark session. That's something also what you will learn in the assignment a bit more, and that we will elaborate a little bit more in practical lecture 3.1. So here it's a bit dry, but usually from the Spark session is something where you start everything in Spark, right? You create then from there data frames that you read in and bring it to the Spark session. And that's something, of course, we will look a little bit more when we then have our practical idea. But this is how you start basically with Spark. You have a Python Spark, let's say, binding that you can use using here ML-lib parts, for instance, or SQL parts as these libraries on top of Spark. And basically have then with this yarn, you remember that was a scheduler, the grip on the Spark runtime. And from there, you can do quite lots of nice things. And we will look in this a little bit more when we have then our practical. So I'll go here a little bit quicker. This is one application where you have, of course, also the possibility now to basically combine this with different ideas, how you have the APIs for data. So data frames, pandas, as we discussed also in our first couple of lectures with Jupyter and Python. So huge flexibility is, of course, Python also suggests what you can use here. Here's another one with Wordcount, where you see basically if you have lots of different, let's say, documents, want you just throw to some Apache Spark installation, then you basically can here see we can do this very quickly of just, basically have a couple of lines in PySpark, and no matter how much documents you would have, the driver just needs more worker in order to differentiate the work and cut off the work. And then with this MapReduce, we'll be working like splitting lots of these data in small, and we'll just do simple operations like count, right? 2 was once, B was once, all was once. And just at the end of it, there will be a summary statistics while you have distributed this a lot and get lots of feedback from all the simple operations, how often it was counted, and then get the overall result. And this means you can basically look, for instance, in 1 terabyte of data in 5 or 7 seconds, right? While your laptop would be much more harder to look at 1 terabyte. Of course, if you have enough workers and scale up, then you can make that happen. That's basically all I wanted to give you in the first part. I have a nice summary here of the video, and then we break for 10 minutes.
Runtime architecture of Spark application. In this video, I'm going to explain about the runtime architecture of Spark application. By the end of this video, you will know the internal details of how a Spark application runs. Apache Spark uses master-slave architecture. The client submits a Spark user application code. When an application code is submitted, the driver implicitly converts user code containing transformations and actions to logical directed acyclic graph, DAG. At this stage, it also performs optimizations, such as pipelining transformations. Then it converts the logical graph, DAG, into physical execution plan with sets of stages. After converting into physical execution plan, it creates physical execution units called tasks under each stage. Then the tasks are bundled to be sent to the cluster. Now, the driver talks to Cluster Manager and negotiates for resources. Cluster Manager launches executors in worker nodes on behalf of the driver. At this point, the driver will send the tasks to the executors based on data placement. When executors start, they register themselves with the driver, so driver will have complete view of all executors. Executors start executing the tasks assigned by the driver program. At any point of time, when the application is running, driver program will monitor the set of executors that runs. Driver will also schedule future tasks in appropriate location based on data placement. The user program may cache data in certain locations using cache method or persist method. Driver tracks the location of cache data and uses it to schedule future tasks that access that data. Driver exposes information about the running Spark application through a web UI at port 4040. So, if you are running the application in localhost, the web UI link will be http://localhost 4040. When driver's main method exists or when it calls Spark context stopped method, it will terminate the executors and release resources from Cluster Manager. In this video, we saw the runtime architecture of Spark application and how a Spark application runs when a job is submitted. In the next video, we will learn about RDD, which is the Spark's core system.
All right. Yeah, I think we break here for 10 minutes and then come back to the second part.